Hello everyone. I'm Sebastian Rosentraeter from Leybold Vacuum. We're a supplier of vacuum pumps and vacuum systems, and for the last years we've been in contact with, I would say, most Hyperloop startups or Hyperloop companies. So you can see here the two biggest ones we've supplied with vacuum pumps up to now. So the test tracks of Virgin Hyperloop and Hyperloop TT. So what do we usually get when we're talking to Hyperloop customers, being it bigger companies or university or startups? We usually get, first of all, a request for a pump down time of a big tube. So it's anywhere from a couple of meters long and wide to up to like roughly 500 meters. Sometimes then the next thing is operation pressure. So usually there's a target of 1 millibar or maybe a range of different pressures. And then we get an assessment of the leak flow or the leak rate of this tube, which is then coming to a point where it's rather difficult. So this is where it gets tricky. And although we already have quite huge test tracks right now, these test tracks cannot answer all questions which we see for vacuum technology here. So we need bigger vacuum test tracks to investigate certain features, and I think HARD is doing a good job and going towards that. So we need to think big even for vacuum systems to answer the questions there. So one thing is, and here after lunch is always good to talk about vacuum physics, right? So we have here the Maxwell-Boltzmann distribution of different gases, so the biggest components of air. And what we can see here is that at the target speed of Hyperloops are roughly 300 meters per second, so up to 1,000 kilometers per hour. We're already quite faster than a lot of gas particles inside the tube. So, and what does it mean? So it means we have a pressure buildup, a substantial pressure buildup in front of a pod. And is the average mean free path, so basically the distance between two molecules until they hit each other, is still much, much smaller, even under vacuum, than the size of the gap surrounding the pod. We still have viscous flow, so there will be a flow phenomena, and we have a pressure difference. So what we can also see here on the dashed lines, I think maybe it's a bit hard to see here with the light, is that this pressure buildup is temperature dependent. So if you have lower temperatures, the pressure buildup will be higher than at higher temperatures. This can cause some problems for vacuum pumps and for the propulsion. And what can we as Leybold do here? So of course, we are no experts in doing complex 3D fluid dynamics around the pod. So this is not our core business. We're not doing CFD for designing vacuum pumps. There are other simulation techniques involved which are being used. But what we can do very, very good is do ring gap approximations and flow through small gaps through holes. This is our core competence when designing vacuum pumps. And this is what we can also use here to get a first assumption of how big such a pressure difference is. So if we just use here the pressure inside the tube, so the nominal operation pressure P1, then we have a flow across this gap, a volume flow, which you can calculate by V, the velocity of the pod, times the section area of the whole tube. So here we have R times R square P. And this flow needs to go through the gap around the pod. So, and as I said, we're quite good in analyzing this and calculating this. So we have here a qualitative estimation of the pressure buildup in front of such a pod. And we can see if we're going to low pressures and a rather small gap size, so this will be the gray column in the back, that there's a quite substantial pressure buildup. So we can see with a 0.2 meter gap, we're talking about the 4-meter pipe here in a diameter, so then the pot would be 3.6 meters in diameter. We already have a pressure increase by factor 4, almost factor 4, 4.1 millibr, and still roughly 2.5 the pressure build up for 1 millibar, which what we see right now seems to be like the target pressure that most Hyperloop companies are looking to. So we've compared this with calculation and also testing from our partners, and this is a reasonable number in terms of quality. Of course, it really depends on the shape of the pot, and we know the tube is not a perfect circle, so there will be differences. So of course, in reality, it will be slightly different, but the effect can already be assumed quite easily. So what are we using for vacuum pumps? And then here you can see why we have this this knowledge. We propose to use dry vacuum pumps. So you can see here co-rotating dry screw pumps, and you can see the inner compression inside the pump. And these are actually not contacting these rotors. So there's a fine gap which we have to calculate, and it's the same calculation principles that we can use to assume the ring gap analysis. So these are pumps that would compress the air, and it's mostly air what we're talking about, towards atmosphere. They're really efficient during pump downs, but they're not really the best for maintaining low pressure operation. For these we advise to use and will always choose these roots piston pumps. So you can see the internal volume is quite huge in comparison to the small gaps of the screws. And you have a lot of pumping speed, you just don't have a lot of compression. So we propose to use multi-stage systems where we have a pre-compression with these roots pumps, and then the resulting volume that needs to be pumped away by the 4 pumps is just roughly, you could say, 10% of what is initially coming as leak flow. Oh. So, and how do we size such a system? So we have these pumping speed curves here. You can see for such a dry screw pump, it's designed to have an optimum pumping speed at 1 millibar. But it takes a lot of energy to pump. So if we use, this is just for comparison here, 4 of these dry screw pumps, we have roughly a pumping speed of 1,800 cubic meter at 1 millibar. Or we can do the same thing by just using one of these blowers, these roots pumps, and stack it on top of the dry vacuum pump, of the dry screw pump. And then at 1 millibar, you can see we're even at higher vacuum, at higher suction speed, at a much lower power consumption. So you can replace 3 of these 4 vacuum pumps by just one rough vacuum pump. The only thing what you can see here is you can only really operate the first stage, so the blower stage, below 20-30 millibars. So that's the only point where you can basically start it working. You can also use a VFD, and then you have a slight upwards curve, but still they're only working at low pressures. So in the end, for designing a Hyperloop system, we're talking about a system that quite looks like these. So it's not exactly one of the systems we supply to Virgin or HTT, but it's a much similar looking system. So we have actually 3 stages. So we have all the roots blowers on top. We have here 2 roots blowers. And then here, these are all dry screw pumps. And actually, it's always 2 stacked on top of each other. And for a pump down, to actually pump the gas at high pressures to the desired, in the desired time, we actually need all the pumps that you can see here. And just if we go down to low pressures, and it's only about maintaining pressure, then we can just switch off a lot of these 4 vacuum pumps. And as I've shown before, these are the ones that are taking all the energy. And we can pump the leakage with just these very energy efficient roots pumps and just one set of these dry screw vacuum pumps. So one thing, I hope I still have some time for that. 2 minutes should be enough. So coming back to the ring gap, what happens if a pot passes a vacuum system? So we all know we need these vacuum systems spaced over the whole track. So in intervals, I think it's still open how big these intervals or sections will be. And if such a pod passes a vacuum pump system, the vacuum pump system will see a pressure shock. So, and this pressure shock can, if the pump system is designed poorly, result even in possible damage because of the multiplied compression of these stages, or at least what it will do is it will slow down the pumps. So you can see here the pod is coming, we have a pressure peak, and then I'll just quickly go through this. The four pump don't really care, but the higher, not the higher, sorry, the blowers, they are slowed down because of the additional pressure. So I'm not showing the whole simulation here, it needs to be too much time. What you can see here, and we're looking now just at the lower diagram to speed it up. We have here the operation before the pressure shock, and then the pod passes, and because of this pressure shock, the pumps need to be slowed down. So otherwise, you would have to use way, way bigger motors, so they wouldn't have to slow down, but then overall, the performance would be the same, but the power consumption would be too high. And what you can see here, it takes roughly, well, you can say up to here, so 60 seconds until the pumps are really at full speed anymore, again. And what does it mean is you actually have to oversize a vacuum system for if you're talking about these pressure shocks, because the pressure shocks will mean you will gradually slow down the vacuum pumps. And if you imagine 60 seconds, the next pod passes maybe after 30 seconds, you will have the vacuum pump slowing down even more until you finally reach a certain pressure level, not pressure, but rotation speed, which would be kind of stable. So pressure shocks can cause a problem for vacuum pump systems, and more so what you could do, I'm not going into detail about this slide here because it takes too much time. What you could do is just design for that, and you just speed up the vacuum pump system just before the pod comes. You know when the pod is coming, you can just speed up for that time, just knowing that just this pressure shock will slow down the vacuum pumps again. And by that have a much more energy efficient system than over-designing it in the first place. So, what can we take home? So we have investigated a lot of possible vacuum challenges and also things that are not really directly involving the vacuum pumps. So the vacuum pumps actually, they just need to pump air for pump down and maintaining pressure. That's what they are designed to do. That's not difficult. It's just sizing the system and dealing with what is coming from the system, like pressure shocks, and how does the vacuum system react to that. So, last slide, what I talked about is even thinking about vacuum on demand, like only speeding up the vacuum pumps if you need them to be at full speed is a thing which you could do. So, to conclude, the vacuum pumps are there, we are ready, so make sure we need to sell more of these. Thanks.